Hi, welcome to lesson 18a, the area under a curve. We worked a couple days ago on finding areas of common shapes like rectangles and triangles and composition of figures, and we then used those basic formulas to find the total areas. What we're going to do today is we're going to try to find the area under a curve where it's not as straightforward as those other shapes. So way back when, Archimedes actually found the area under a curve using a technique that we're going to use right here. So take a look at this function here. This is the function y equals x squared plus 1. And we'd like to try to find the area under a curve. So if you look at this, if we wanted to find the area below the curve, above the x-axis, and between x equals 0 and x equals 2, we would find that near the bottom part we could maybe look at this as a large rectangle, and then here could be another rectangle here, maybe another rectangle here, and then start looking at filling in these gaps. There's little curved portions. They could slightly resemble a triangle, but they're not quite triangular because of that curved line here. So what was done by Archimedes was he took this the curve and he decided, okay, well if I know the area of a rectangle, why not create rectangles underneath this curve? So we could take this and say, okay, well here is the left edge of the rectangle, and I'm going to draw this right up to the bottom of the curve here. So this vertex of the rectangle corresponds to that point on the curve. So here we've got the first rectangle. Then what we'll do is we'll create a rectangle where the upper edge of the rectangle corresponds to this point on the curve. And so we'll form the rectangle like this. And we'll do the same thing. We'll find this point on the curve, and we use that as the upper left vertex of this next rectangle. And then we'll do the same thing right here at this point on the curve. Okay, so we have 4 rectangular strips here, and the upper left vertex of each of these rectangles corresponds to a point on the curve. The uppermost edge of the rectangle corresponds to the minimum value on any interval of the width of each of these rectangles. So if we look at this width here, this width has an interval between 0 and 1/2. So width is a half a unit. So on this interval, this point here, this top part of the top side of the rectangle corresponds to the minimum y value on this interval, which is right here. On this next interval, from 1/2 to 1, there's 1 right there. On this width, or this interval, this point corresponds to the minimum value on this interval. So from x equals 1/2 to x equals 1, that's the minimum value on this interval. When we look at this next width, from x equals 1 to x equals 3/2, again, this vertex, this point, the y value corresponds to the minimum value on this interval, and then so on for here as well. That's the minimum value here. Okay, so what we can do now, these are what we call lower rectangles because they are all below the curve, and you can see there's some extra space above the curve, above the rectangle in any interval that's not accounted for the area. So there's a fair amount of space in here that's not accounted for, but these are the lower rectangles. Okay, so what we're going to do then is, if we've already kind of discussed this a little bit, what's the formula for each area of the rectangle? Well, we know the area is length times width. I'll write it as width times length just for this case. And what is the width of each? Well, of these ones, in this case, we see the width is going to be, well, if there's 1, 2, 3, 4 strips, the whole interval from 0 to 2 is divided into 4, so the width is the full interval divided by the number of strips, which is 1/2. And how do we determine the length of each? So if we look at the length here of this, that corresponds to the height from 0 up to the to this point on the curve. So how would we find the y value of this point on the curve, or the y value of this point on the curve? The y value, of course, corresponds to the height of this rectangle, rectangle number 2. And then how do we find the length or the height of this rectangle? Because that corresponds to the y value of this point on the curve. Well, we'd have to just basically substitute these values into the function. So it would be basically f of x. So the length of each of these rectangles would be just f of x. So whatever the x value is that corresponds with this left side of the rectangle, or that point, will give us the length of each of these rectangles. Okay, we know the width, it's standard here. Now we know the length. Okay, so if we were to flip over to the other side here, we're going to look at this. So we've got, if we want to calculate the area of the lower rectangles, we do width times length. Well, the width is 1/2, we know that, and the length is going to be f of x. Well, if we look at the very first interval, the x value is 0. The function is f of x, which is equal to x squared plus 1. So we've got 0 squared plus 1. Okay, that's the length of the first rectangle. The second rectangle is again the width of 1/2, and then for the length we know that this x value is 1/2. Right here, that's 1/2. So that y value, which corresponds to the length of this rectangle, is calculated by doing f of 1/2, which is 1/2 squared plus 1. Then again, the width is 1/2. This is for the third strip here. So the height or the length of this rectangle corresponds to this y value, which is f of 1, which is 1 squared plus 1. And then again for the fourth rectangle, the width is 1/2, and we're substituting the x value of 3/2, which corresponds to this y value, or this length of that rectangle there. So that would be 3/2 squared plus 1. Okay, and then we just do this calculation. I'll put a little extra step in here, so we got 1/2. Well, 0 squared plus 1 is just 1. Plus, we got the width of 1/2. 1/2 squared is 1/4, plus 1, 5/4. Plus we got 1/2 again for the width. 1 squared plus 1 gives us 2. And then 3 squared is 9 quarters plus 1, which gives us 13 quarters. And when we add all those things up after we do those products, and then get a decimal form for it, we end up getting 3.75 square units. Okay, so those are the lower rectangles, but we know that that can't be the actual area under the curve because there's this empty space above each of those rectangles. So the lower area is, of course, lower or less than the actual area under the curve. So what we're going to do now is we're going to draw some upper rectangles to make sure that we kind of cover our bases here. So the upper rectangles now is going to be the same thing, except that we're going to now use the maximum value on this interval. So we're going to take, so for this first interval here from 0 to a half, we're going to draw the rectangle so that the upper right vertex of the rectangle is at the maximum y value on this interval. So the interval goes from 0 to a half. The maximum y value is right here. So we're going to draw the rectangle here. So now I'm drawing the upper rectangles. And then for this next interval from a half to 1, we use the maximum value on this interval from a half to 1, and that goes up to this value up here. And so we've got this y value. So we get that rectangle. And then we do the same thing here. This is the maximum value on this next interval. And then we'll do that one more time. The maximum value on this last interval goes up to here. And we've got the rectangles like that. So now we see these are the upper rectangles, and notice now each of these rectangles is got some extra space above the curve. Okay, which hopefully we'll be able to then average out over the time. So now what we're going to do is we're going to do the same sort of thing. Each of the lengths of these rectangles corresponds to the maximum y value on each interval. And again, that corresponds to the y value of the curve at that point, which corresponds to the x value of each of those subintervals. So now instead of starting at 0, we're now starting at the next, the higher value on the interval. So in this case it's going to be a half. Then we're going to substitute in 1 to get this length of this upper rectangle. Then we substitute in 3 halves to find this height or this length of this upper rectangle, and then we're going to substitute in 2 into the function to find this height or that length of that upper rectangle there. Okay, so we're going to follow the same pattern again. Each rectangle is the width of a half. Then we substitute into the function 1/2, because that's the x value that corresponds to the right edge of this rectangle right here. This is a half for this first rectangle up here. And when we substitute in a half into this function, we get the maximum y value on this interval. And then we'll just continue that. So we've got a half multiplied by 1 squared plus 1, then a half multiplied by 3 halves squared plus 1, and a half, which is the width, multiplied by 2 squared plus 1. And then we can just simplify this again. So the width is a half, the length is going to be 5 quarters, plus a half multiplied by 2, 1 squared plus 1, plus a half, 3 halves squared plus 1, is 13/4 plus a half, and then we've got 2 squared plus 1, which is 5. And then when we add all these together, we end up getting 5.75 units squared. Okay, so we see now that the upper rectangles have extra area that is above the curve. So the sum of these rectangles, the upper rectangles, has to be greater than the actual sum of the area under the curve. So we know that the lower rectangle sum is less than the actual area, and that is less than the upper area. So the area under the curve, x squared plus 1, between x squared plus 1 and the x-axis on the interval from 0 to 2 is between 3.75 units squared and 5.75 units squared. Okay, so that's 2 units squared of area, of difference between the lower and upper areas. So we need to refine this somehow. How in the heck could we make this, the difference between these, a little bit smaller if we're to continue with the same technique? Well, we could probably divide these rectangles in half to have a smaller, narrower rectangle. So when we break this into a half, this second rectangle now, which is smaller, the left edge of this rectangle, the second rectangle, would then go up to the curve. And then if we did the same thing here, we break this in half, then this rectangle, this half of the rectangle goes up to the curve here, and we break this in half. This goes up to the, so if I'm drawing all the lower rectangles, so it's just a quick sketch here to show that, notice now that the areas that are extra are much smaller than they were in the first estimate with the wider rectangles. So if we continually divide the rectangles in half and make the widths smaller and smaller, we'll be able to get a much more accurate estimate for the area under the curve.